Hello there, Steven here. Today, I give an outlook and look at the development of AI technologies in the field of practical federated learning on mobile devices. We first start with the basic concepts. AI, or artificial intelligence, refers to artificial machineries that resembles human intelligence either in terms of their functionality or behavior. And machine learning refers to intelligent agents that can adapt to previously unseen situations based on data from the past. Federated learning is a kind of machine learning that allows multiple intelligent agents to collaboratively train machine learning models using their local data. The main difference between federated learning and traditional centralized learning is that in traditional centralized learning, all the training data are transferred to the central server. Therefore, there is no data privacy. In federated learning, the data are kept local. We can look at some of the opportunities and challenges that federated learning on mobile devices faces. First, federated learning on mobile devices are useful because there is an increasing high demand for machine learning training data by companies and research. And they cannot just obtain these training data directly, primarily because of the stricter and stricter privacy regulations. With federated learning, they can leave the data on the device and still use them for machine learning training. But also these data that we can obtain on mobile devices, they're usually at the core of many machine learning problems, making them actually valuable. On the other side, federated learning on mobile devices has many drawbacks. First of all, mobile devices have much lower performance in terms of computation, and they also have other trouble like battery issues, internet connection, etc. The heterogeneity problem refers to the problem where mobile devices contain very different data and they have very different computational speed. These problems would make it harder for the model to converge and make it longer for the model to converge. Also, training machine learning models on the mobile phones are very difficult. Now, we need to look at the general procedure to see why some of these challenges are there. To start with, this is the general procedure. We have a bunch of training iterations, and for each training iteration, our server distributes the global model to clients where they train the models using local data and create locally trained models. Then they need to send the models back to the server. The server aggregates these local models into a new global model, and the process repeats. As we can see here, this process starts from a global model distributed to clients, trained with local data into locally trained models, sent back to the server and aggregated. So here we see the main tasks. We need to schedule when to send the global models down and how to collect them back. There's communication overhead. We are sending the models around, and we need to train the machine learning model on the mobile device. One of the concrete examples of how we deal with these tasks is the first federated learning algorithm, Fed-average. Fed-average samples a portion of the client in each iteration and only do local training with them. The local training is just a stochastic gradient descent, and it does the communication by sending model parameters, which they denote W. The server aggregates the parameters just by taking weighted average. And also, the server waits for every single selected client to complete. Okay, now we see some of the issues from this strategy. In the scheduling, because server waits for everyone to complete, when some specific devices are extremely slow, much slower than others, the server still needs to wait for them. That is called the straggler. And the straggler problem means that the slowest device would likely become the bottleneck of the problem. We also have communication issues because mobile devices run on Wi-Fi or 5G or something. They have low bandwidth and network reliability. On-device training itself is a problem, but also if we use different machine learning frameworks, for example, on Android and iOS, we have parameter alignment problem. So our W's will be different. Now let's look at the first problem, scheduling. Here we see that we just sample clients, wait for them to complete, and then take weighted average. To address the straggler problem that this approach addresses, we can set a timeout so we don't wait for devices that are too slow in this round. But this is not actually applicable because some mobile devices are inherently slower, and this way their data would never be used. There are some algorithms like FedProx that sets a different local number of epochs for each client. So the slower clients can do less work each round, catching up with the global pace. There are also asynchronous federated learning where there isn't a strict idea of iterations. They just train the model and try to aggregate local models. Usually, the best way of the scheduling is done by doing simulations and benchmarks. These simulation frameworks usually allow you to write the whole problem out in Python. And to put it into production, usually the federated learning frameworks such as FedML Flower provides programming interfaces or abstract classes or protocols called in some languages. And you can implement your custom server and clients against these interfaces. The server is usually written in Python, and clients have to be written in Java, Kotlin, Swift, Objective-C. Here's an example from Flower for the kind of interface you would expect for a client to implement. And here is a screenshot from FedML. Here is how they allow you to customize your server. They give you a set of APIs so you can write a Python program and upload that zipped program. They also provide a GUI to set some of the parameters. Now, let's look at communication. Think about mobile devices. They communicate over probably Wi-Fi when they're doing the federated learning, and it's low bandwidth and unreliable compared to centralized servers. So the first thing you want to do is you want to minimize data transmission. And traditionally, this is done by only transmitting the difference between the parameters W. Some parameters are not changed, so those work can be saved. But also, there are newer research that chops down the neural networks they train into subnetworks, so they only need to transmit the subnetworks. However, this would be very challenging to implement in practice because you're doing mobile development, you're writing this in Java or Swift. In practice, communication is usually implemented using remote procedure calls. This is a way to execute code in a remote partner by sending them messages. The benefit is it's much easier to customize the scheduling strategies using RPCs. Here are some popular RPC frameworks that are actually used. We will talk about gRPC for the most, and it is actually representative over the other ones. gRPC uses protobuf, which is a binary format, so it is small in transmission size. It supports multiple languages, so you can do mobile development and also write the server in Python with gRPC. And it is based on HTTP2, which means it bypasses firewalls and proxies. The HTTP2 connection means that the server knows when clients are dropped, they lost connection, and it can also mean that the server can push instructions to the clients to ask them to train. The last problem is on-device training, which is still a large problem, as you can see from the comparison among federated learning frameworks. Most frameworks don't support on-device training at all. Some frameworks do have partial support, but we also need hardware acceleration for the on-device training to actually be feasible. The first option frameworks can choose for on-device training is using first-party frameworks for mobile federated learning. This means TensorFlow Lite for Android by Google and CoreML for iOS by Apple. The upside is that they are sort of natively supported by the operating system vendors themselves. They have the best hardware acceleration. For example, CoreML is the only framework that we know of that can leverage the neural engines on iPhones. The cons is that you need two implementations on Android and iOS. They produce different parameters. You are having a hard time to aggregate across platforms. This means some of the federated learning frameworks would have two sets of on-device training and they cannot interrupt. The other cons I didn't list here is CoreML being proprietary is very hard to deal with. We also have third-party mobile machine learning frameworks. For example, FedML uses MNN by Alibaba. It claims that it supports iOS, but I haven't seen FedML's iOS SDK, so something has gone wrong. Sift has its own Android and iOS implementations, but they haven't been touched for 2 years and they only use CPU. Onyx Runtime by Microsoft is coming up. They just had their iOS support in September and they only use CPU. So the biggest problem is they are not well supported and their development is not guaranteed. We also have some interesting solutions that are actually not for mobile. For example, TensorFlow.js targets the web. It uses WGPU to accelerate. We've seen examples where people use React Native with TensorFlow.js, but they have a problem to do the evaluation. FedScale used Termux to get a Unix terminal environment on Android, but Termux is itself an app, and embedding FedScale into other apps is not really applicable. Lastly, let's talk about the actually used mechanism in federated learning, which is model personalization. Usually, they just send a pre-trained model to each devices and use their local data to train the model to fit that person better. They only train the model partially. Usually, they only train the last layer of the neural network, for example. This means that they can use much larger machine learning models. Now, let's have some discussions. So if we look at the mobile federated learning timeline, it was born in 2016, and the first effective application is Gboard in 19. In 21, we saw widespread simulation support by frameworks like Sift, and in 23, we see many frameworks like FedML and Flower to support on-device training on mobile. And there's no way to see when there will be widespread adoption. We have seen the advancements in scheduling strategies and communication that would make federated learning more practical. The number one roadblock is still on-device training. And I haven't talked about security issues. Federated learning is attackable, and there are protections like homogeneous encryption, secure multi-party computation, and differential privacy, etc. So here are some closing thoughts. Mobile operating system vendors, Google and Apple, might still have a monopoly on federated learning on mobile devices because they are the ones controlling the OS. Although federated learning preserves privacy, we can never know when data is sent into the app that they are actually used for federated learning, not to mask for direct data collection. That is a very difficult ethical issue. And the key to have a bright future for federated learning on mobile is an open community. We've now seen a lot of federated learning services that are proprietary, and this is a bad sign. Here are the summaries. If you are interested in some of the materials, feel free to check out the report and the references. Thank you.